Hello students, welcome to the electrical engineering channel. In this lecture, I am going to demonstrate the mathematical modeling of a synchronous motor to calculate the power developed at the rotor shaft. So for calculating the expression for the output power which is generated by the synchronous motor, we have to draw the phasor diagrams including all the parameters which are associated with a synchronous motor. So this is the applied voltage vector starting from this point O to point A. The back EMF vector is actually starting from this point B to this point A, and this is EB dash. This is the convention which we have used from the previous discussion, and the vector from this point O up to this point B, or the vector from the tail of this applied voltage vector to the tail of this back EMF vector, is the reactance voltage vector ER, and this is the orientation of the armature current vector, and it is lying at almost 90 degrees with the reactance voltage, but normally it is actually slightly smaller than 90 degrees due to the resistance of the armature winding. So this angle is theta, and this angle is alpha, the angle between this applied voltage and the back EMF. This angle is phi, the angle between the applied voltage and the armature current, and this angle is assumed as psi. So psi is the angle between the back EMF and the armature current. Now we have to draw a vector which actually passes through this point B, and this vector is lying at an angle theta with EB, this back EMF. So while drawing this vector BCD or CBD, we have to take care that the angle between this vector and this back EMF vector is equal to theta, and theta is the internal angle, and theta is the angle between this ER and IA. So we have to maintain this same angle between this CBD vector and this back EMF vector. So why we are doing this, it will be clear in the proceeding discussion of this lecture. So this is theta. Now we have to draw a parallel line AE. So this vector AE is parallel to this vector CBD, and now this angle is equal to psi. So this angle between CBD and this ER reactance voltage is also equal to psi. So why these two angles are same? So line CBD is drawn at an angle theta with EB. Angle between EB and IA is psi. That is, angle between IA and EB is equal to psi. Now from this figure we can see that the angle between the reactance voltage and IA is equal to theta. So the angle between this reactance voltage and IA is equal to theta. Similarly, the angle between CBD and EB is also equal to theta. So the angle between this CBD and EB, this angle is also equal to theta. So if the angle between this EB and IA is equal to psi, now the angle between this ER and CBD will also be equal to psi, because the angle between these two vectors and these two vectors is same. So if the angle between these two vectors is psi, the angle between these two vectors will also be equal to psi. So the angle OBD is also equal to psi. So this OBD, so this angle will also be equal to psi. And now we have several triangles which we can observe in this figure. So from this figure, the mechanical power generated by the synchronous motor is equal to back EMF times this armature current multiplied by cos of angle between them. So EV into IA cos psi is the mechanical power, and we have to simplify this expression. So in this triangle OBD, so this is one triangle OBD, and here BD is equal to ER cos psi. So this is BD, this angle is psi, so this component is equal to ER multiplied by cos psi, because the component in front of the angle is always the sine component, and the component with this angle is always the cosine component. So this BD is equal to ER cos psi and ER is equal to IAZS. So this will become IAZS cos psi and this BD is equal to CD minus BC. So this BD is equal to CD minus BC and CD is equal to AE since these are the parallel vectors. AE and CBD are the parallel vectors. So CD is equal to AE. So this BD will become AE minus BC and AE is equal to, from this triangle we can evaluate this AE. So this is V. Now we have to first find out this angle between V and AE. Now these two vectors are parallel, CBD and AE vectors, they are parallel. And this is one vector starting from this point B up to this point A. So if this angle is theta, this total angle will also be equal to theta. And this angle is alpha, so this angle will become theta minus alpha. And this is a right angle triangle. And from this triangle, we can calculate AE. So AE is equal to V times cos theta minus alpha because this will be sine component and this will be the cosine component. And next term is BC and BC can also be calculated by assuming this right angle triangle and here BC will be equal to EB times cos theta. So this is the new set of equations which we have obtained. So BD is equal to AE minus BC and this is IAZ as cos psi equal to V times cos theta minus alpha minus EB times cos theta. And we can divide this whole equation by ZS. So it will become IA cos psi equal to V over ZS cos theta minus alpha minus EB over ZS cos theta. And PM, the mechanical power is equal to EB times IA cos psi. So we have to multiply this right hand side with EB. So it will become EB into V over ZS cos theta minus alpha minus EB square over ZS cos theta. So this is the expression for the mechanical power and we can calculate the generated torque by this power expression and power is equal to T omega and omega is equal to 2 pi ns. Ns is the synchronous speed in RPS and we can divide it by 60 to get ns in RPM. So PM is equal to 2 pi by 60 ns Tg. Tg is the generated torque and Tg will be equal to 60 over 2 pi ns into PM and 60 over 2 pi is equal to 9.55. So it will become 9.55 into PM over ns. Normally, this internal angle is approximately equal to 90 degrees, as I have already told that this internal angle theta is almost equal to 90 degrees if we ignore the armature resistance. Otherwise, it will be slightly smaller than 90 degrees, for example, 88 degrees, 87 degrees. But still, we can approximate it as equal to 90 degrees. So, in this case, this cos theta will be equal to 0 and it will become cos 90 minus alpha and cos 90 minus alpha is equal to sine alpha. So PM is equal to EB into V divided by Z as sine alpha. This is the simplified expression of the mechanical power. The maximum power will be equal to EB times V divided by ZS and the generated torque is equal to 9.55 divided by NS into this PM expression and mechanical power is equal to EBV over Z sine alpha and maximum torque will be or pull out torque is equal to 9.55 over ns into Pmax and Pmax is equal to EBV over Z. So if we plot the maximum torque with against this load angle alpha, it will be a such a curve. So at 0 degrees, the torque will be equal to 0. Similarly, at 180 degrees, the torque will be equal to 0 and torque will be maximum when we have a load angle of 90 degrees. Based on this discussion, we are going to solve a numerical problem to calculate the mechanical power generated by the synchronous motor, armature current drawn by the motor, back EMF, load angle, and the pull-out torque. So this is a 75 kilowatt three-phase 50 hertz synchronous motor operating at 440 volts line voltage and at zero point 0.8 power factor leading. So remember this 75 kilowatt is always the output power generated by the synchronous motor. And first we have to calculate the synchronous speed, which is equal to 120 f over p. So this is 1500 rpm. The mechanical power is equal to the input power if we ignore the stator copper losses, and input power is equal to output power divided by the efficiency. So 75 kilowatts divided by 0.95 will be equal to 78,950 watts. This is the mechanical or the input power. Now this input power is equal to under root 3 times VLIL into cos phi. Cos phi is 0.8 leading, 0.8 power factor leading. Under root 3 times VL into IL. VL is equal to 440 volts, and IA is the quantity which has to be calculated. So from this expression, IA is calculated to be 129 amperes. And the phase voltage can be calculated from this given line voltage, and applied phase voltage is equal to 440 divided by under root 3. So this will be 254 volts. So the applied voltage is always taken as a reference in the phasor representation of the synchronous motor. So V is equal to 254 with an angle of 0 degrees volts. Now we have to calculate the back EMF, and applied voltage is equal to back EMF plus the reactance voltage, and back EMF will be equal to applied voltage minus the reactance voltage. Reactance voltage is equal to ER, and ER is equal to J times I times XS. So XS is the stator reactance. So back EMF will be equal to this is applied voltage 254 with an angle of 0 minus current is equal to 129 degrees, and we are given power factor of 0.8 leading. So this armature current will be lying leading to the applied voltage, and the angle can be calculated by cos inverse 0.8. So cos inverse 0.8 is equal to 36.9 degrees, and whether we will put a positive sign or negative sign with this angle, it will be determined by the nature of power factor. Since the power factor is leading, so this armature current will be leading the applied voltage vector. So we will have a positive sign over here, and then this is the stator reactance, and it is equal to 2.5 ohms with an angle of 90 degrees. So since we have J over here, so the effect of this J can be applied in this angle. So this J corresponds to this 90-degree angle in the argument of this reactance value. So when we solve this phasor, we will end up with 516 with an angle of minus 30 degrees, and this is the value of the back EMF. And now the back EMF always lies at an angle of alpha with the applied voltage. So this is the back EMF angle, and it is equal to alpha. So alpha is equal to minus 30 degrees. So we have calculated the armature current, the back EMF, and also the load angle. So the mechanical power is equal to 3 times EB into V divided by XS into sine alpha. So pull out torque can be calculated by first calculating the maximum power, and the power will be maximum when this alpha is assumed as 90 degrees. So the sine alpha will be equal to 1. So we will just have to calculate this expression. So three phase power will be given by 3 times back EMF into voltage divided by XS, and it will be given as 157 into 275, 157,275, and this is the maximum torque or the pull out torque, and it is equal to 9.55 into PM divided by ns. So this is the synchronous speed, and when we calculate and or when we solve this expression, so this is 157 to 75. There is no dot over here, so this dot is put by mistake. So there is no point over here, and when we solve this expression, we will get 1000 Newton meter as the pull out torque. So that is all about our today's lecture. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.